Ted, hi, good to see you again. Been a
Can
while.
you see and hear me?
I can see and I can hear
Awesome.
you.
Great.
Listen, I'm gonna leave you to present. Good to see you again.
Okay.
Taj is here
I'm
to
gonna
present scalability through
screen share
Utreexo.
somehow. How's this gonna
Right.
work? Screen share?
Yeah, that's it.
Yep. Um, hi. I can't see you, but you can see me. So this is, I guess, my first sort of virtual conference. Getting used to it, but yeah, sounds fun. I'm going to present about Utreexo. It's a bit technical. I'll try to make it sort of, there may be a varied audience of levels of technical knowledge. And I'll mention some of the things that were mentioned by Pierre a bit before. So first, a little intro. I'm Taj Raja. I work on Bitcoin at the MIT Digital Currency Initiative. Neha spoke earlier. You might have seen, hopefully, her. So I work with Neha. Previous papers I've worked on. So I wrote the Lightning Network paper with Joseph Poon, discrete log contracts. That was about 2 years ago, which is a smart contract platform on Bitcoin. And today I'm here to talk about Utreexo, which I've been working on for a bit over a year. So scalability is been a concern for Bitcoin for a long time. In fact, it's the first thing anyone ever said about Bitcoin. And if we look, so Pierre mentioned you got to download 400 gigs. I think it's more like 300, but yeah, it's a lot. If I checked this just a day or two ago, if you go into your Bitcoin folder and you're running a full archival node, it's about 300 gigabytes of data in total. But if you actually look at how it works, there's 300 gigabytes of blocks, that's the blockchain, and then this 3.8 or 4-ish gigabyte chain state. And what that is the who actually owns what. So that's a list of all the Bitcoins and where they are. So it's the 300 gigs is actually everything that's ever happened. That's not, so some people call it the ledger, but a better metaphor would be the history, right? So it's the history of everything that has ever happened in Bitcoin. But in order to check what's going on next, you don't need to know necessarily everything that ever happened. You just need to know what the current state is of who owns what right now. And that's much smaller. It's about, almost 100 times smaller. It's about 4 gigabytes instead of 300 gigabytes. And so this has been exploited. You can have a pruned node. Even today, for years, you've been able to, in Bitcoin Core, set it so that you still download and check the whole history, but you don't keep the whole thing. And you only keep, 5, 10 gigabytes. Yeah, so we can discard this after downloading, but we need to keep this 4 gigabyte state, right? So in order to verify future transactions, you absolutely need to know what coins exist in order to verify this. And there's not really any way around that. Well, or is there? So this is something that's been a concern for years, right? This UTXO set is what it's called, unspent transaction output. So how do we, reduce this 4 gigabytes or keep it from getting much bigger? So the Lightning Network is one example where it helps to use UTXOs more efficiently. So instead of creating and destroying UTXOs all the time for transactions, you create one single long-lived UTXO and then do a lot of things with it. And then when you close a Lightning channel, you're getting rid of that UTXO and creating a new one. SegWit, segregated witness, helps. It sort of incentivizes more efficient use of the UTXO set because inputs are more expensive. Sorry, inputs become cheaper than outputs, which makes sense if you want to reduce the UTXO set. So the way to think about it is UTXOs are where the Bitcoins live. They sort of are Bitcoins. I think of Bitcoin in terms of UTXOs, and maybe in 100 years, if everyone's using this, the word money just becomes replaced with UTXO or something. I don't know. And this is a little confusing because a lot of times if you're looking at like web explorers, things like that, it seems that Bitcoins live at addresses, right? The mental model of like, okay, there's an address and Bitcoins go into that address and sort of live there, and then they leave that address. But that's really not how it works on a technical level. Addresses don't have UTXOs. UTXOs have addresses. So the UTXO is where the Bitcoins live, and a UTXO happens to have an address. And two different UTXOs may happen to have the same address, but they're totally distinct UTXOs. Okay, so what are these, on a very concrete level? They're these little small entries in a database. They're tiny. They're like 64 bytes or something. You've got your pub key, the amount, which is 8 bytes, how many Bitcoins are there, and this sort of out point 32-byte hash thing. So they're very small, but there's lots of them. There's about 70 million. And generally, they keep being more of them. You can sort of see on this chart, or you can look at a more updated chart just online, how many UTXOs are there on Bitcoin. And it generally goes up. Sometimes it goes down. So you may have seen like early 2018, it went down. I think a bunch of exchanges were consolidating outputs. But overall, as more people and more entities and there's more usage of Bitcoin, you're going to see this total number of UTXOs go up, which is good. We want adoption, but it's also bad because now our databases are bigger and slower. Okay, so long term, the expansion of the UTXO set is a big concern, right? Pruning helps because what if you only have a 10 gig SSD or something? Well, it's kind of too small. But what if you only have a 128 gig SSD? You can't store the whole blockchain, but that's okay. You can prune, and then you'll have the whole set of UTXOs, and you're okay in terms of consensus. But what if the UTXO set becomes 200 gigabytes or 300 gigabytes? Then you can't store it on your tiny SSD. And also it's a lot of disk I/O is the main thing, because you've got this big database. It's all these tiny little entries. When you're trying to read and write from that, it's a lot of disk seeking. So if you try to run a full node with a spinning hard drive, like a mechanical hard drive, it's extremely slow. And this is a problem. So this problem also exists in other blockchains. So like, I know this is the Bitcoin session, but Ethereum has this problem sort of even worse. They don't have a UTXO set. It's a state set kind of thing, but it's the same idea and it's the same problem, and they've got a lot of disk I/O. So how do you get rid of this? How do you solve this problem? So one issue, one idea is SPV. SPV clients have been around for years and years, but they're not full nodes, right? They're not the real thing. They're not the real deal because SPV nodes can't check signatures because they can't even check that the coins that are being spent even exist. There's also privacy issues and other problems with SPV, but fundamentally SPV isn't doing the validation that a full node does. So one solution, and there's other research on this, but this is sort of my contribution, is accumulators. Not that my contribution is accumulators themselves, but I have a accumulator construction that I think is really well suited towards this problem. So the idea of an accumulator is it's this sort of cryptographic structure where you throw data into it, and then later you can't pull the data back out. It's sort of this bottomless pit or this magic box that you can throw as much as you want in and it still stays the same size. But you can't take anything out. But you can prove things that have been previously thrown into it. And this particular accumulator we're using, you also need to be able to delete from. And in our case, it's kind of tying delete to verify, because the only time you need to verify that a Bitcoin exists is when you're spending it or deleting it. So that's kind of a nice property where you're saying, okay, we actually only need these sort of three functions. We need to add things to it, we need to prove them, and then verify and delete at the same time. So it's this, there's a paper, it's like almost a year old. You can just search for it, it's on ePrint and stuff. It's this hash-based accumulator. So it's basically Merkle trees. It doesn't use any fancy zero-knowledge proofs or pairing or bilinear maps or anything cool. It doesn't even use elliptic curves. It's just hash functions. So if hash functions work, you're good. And if hash functions don't work, we don't live in a world where cryptocurrency is even possible, I think. So I'm not going to go into technical there. But the idea is once you have this, you can run a full node that validates everything, every transaction, every signature, but stores very little data. It ends up being under a kilobyte. However, the downside, so there's of course downside, this is engineering, every transaction now needs to prove that the coins that are being spent exist, because you don't have them on disk. So right now you have the whole 4 gigabytes of who owns what, and when you see a transaction, you look that up and say, okay, yep, there's 3 coins here, and they're spending them. But with this, you don't know what exists, so the people spending the coins need to prove that those coins exist. The issue there, you can imagine a setup where everyone's wallet now contains proofs that their coins exist. And these proofs are not too big. They're less than a kilobyte, a few hundred bytes. And so you could say, yeah, it's their responsibility. If you own a bunch of Bitcoins, you need to, you own a bunch of UTXOs, you keep these proofs that you own them, and you supply those proofs when you're spending the coins. And this seems like a really good way to sort of diffuse and decentralize the responsibility for keeping track of the Bitcoin state, right? So the people who own the Bitcoins now prove them. The issue with that, and this could work, if you're starting from scratch, you could do this. The issue with that is it's very hard to sort of start that, right? If you're the first node using this, you start the software, you download it, and you say, now I want proofs for every transaction. No one else gives you these proofs, right? Because no one's heard of this yet, or some people have heard, no one's running this. So how do you start? You kind of need everyone to switch at once. And so while it's not a hard fork, it is a soft fork, and it's a really tough one because everyone needs to start using it. It's sort of in between a hard fork and soft fork, depending on how you use these terms. So what you need is called a bridge node. And a bridge node maintains, and it's called that because you sort of have two networks, one using the accumulator and one that's the old network that doesn't know about this thing. And so you need a node or several nodes in between to sort of bridge and send messages between the two to make sure they're in sync. So a bridge node can maintain a proof for every UTXO. So it like today's nodes, they keep the entire state, and they also keep this whole set of proofs for the whole state. And that's big, so it's an extra burden on those nodes, but it's not that big. It's like 6 gigabytes or something right now. And so if you have an extra 6 gigs on your SSD, you could say, I want to run a bridge node, and it's not too much extra CPU. So you could totally run it on a laptop, and that's what I do. And this bridge node idea, the bridge node itself is what makes Utreexo sort of unique. There's other accumulator constructions, like using RSA and class groups, that are also very promising, and in some ways better than this hash-based accumulator. But where the hash-based accumulator really shines is it's easy to run a bridge node. It's easy to keep and update proofs for the entire set. It's actually no harder than verifying the regular proofs themselves. So keeping a node in sync and keeping a bridge node in sync are as hard as each other, and you can do it on you can do it on a Raspberry Pi, I think. Well, a laptop. I bet you could do it on a Raspberry Pi. Anyway, okay, so then the downside is you need to supply these proofs, right? So if you're a node and you're syncing this way, how big are these proofs? Well, so if in the naive sense, it's kind of big. Worst case, you could maybe have a block with 20 hashes per proof and 5,000 inputs. You could have 3.2 megabytes. So that's really bad because that would increase the amount of data and amount of traffic 4x. But there's a lot of ways to cut that down. And one is this really nice graph that it's a really nice plot. And let's see. Oh, the bottom, I don't know if it's on my screen or everyone's, but so this is number of UTXOs. And then the bottom here is the lifespan of a UTXO. So what this is saying is, okay, 10 to the 0. So how many Bitcoins only last one block before they're spent? And it's a lot. And then how many last 2 blocks? 3, 4, 10. And then as you go to, last 100,000 blocks, there's not very many that have last any specific length. So what this says is a lot of Bitcoins, I think something like half of them only live like 4 or 5 blocks. So if you can keep in memory the most recent Bitcoins, you don't need proofs for them. They're also really fun is there's these bumps. So there's this bump, I don't know if you can see my cursor, but at 6, so that goes down, and then there's this bump at 6 that is double the size of 5, because everyone waits 6 blocks and then spends their Bitcoins, because I guess in Satoshi's paper he said 6. And then there's a bump at 100, which makes sense because of miners, and then there's this bump at 433. I don't know, it's about 3 days, so maybe T+3. So it's really interesting data. But what's nice about this is you can use this data to you can cache things, right? So what's coming next. You know that these UTXOs are going to be spent soon, so you can keep them in memory, and you don't need to do a proof. So with that, worst case, it would actually be 600 gigs of extra data for IBD. It would triple the amount of data you need to download. But actually, even with proof aggregation just within a single block, it cuts that in half. And then here's a graph of sort of the total performance. And the idea is how much memory do you have to cache at the bottom? And then how much how much data does it take to sync? So you can see, even if you only have like a gig of RAM to dedicate to this, your proofs are now only 40 extra gigs. So you go from downloading 300 gigs to 340, 10, 20% increase. No big deal. I mean, that's what I think. So if you have got a computer and if your internet's really bad and you're like on an airplane trying to sync a full node, this won't help. But in many cases, if you have like a Raspberry Pi plugged into your cable modem, this is great because you don't care so much about the extra bandwidth, but you really do care about the CPU and disk I/O. Okay, so the other thing is with these bridge nodes, it's not a fork. You don't have consensus. If a bunch of people don't like this, no problem. So there hopefully won't be Bitcoin fork rejecting. People didn't like the nightly network, I guess, and hopefully this one, even if you don't like it, well, you don't have to know that people are using it. There's no fork involved. Miners don't have to know. You do need to start with bridge nodes. So I think the way to sort of start this is have the bridge node software, people start running it, and then people start running the clients and connecting to these bridge nodes. So this is fun. This is permissionless innovation. Okay, so what to build? The obvious benefits, you got a smaller full node, but when your state size is so small that you can fit it on a QR code, there's lots of cool things you can do. So you could, for example, if you want to be super trustless, you can sync the entire blockchain on your desktop at home or the laptop at home and leave that on for a day or so, or however long it takes. And then from this desktop, transfer the entire UTXO set to your phone via a QR code, because you trust your desktop, you trust your phone, and you say, okay, well, I'm just going to transfer the whole thing. You can do this today, but today it's 4 gigs, and it's not really feasible. You could copy the whole chain state folder from your Bitcoin thing from one to the other, but people don't do it. They have highly parallel validation, so you could sort of split things up and have multiple computers validating simultaneously. Again, possible today, but it's too big to send this data around. Once your entire state size is small, a lot of cool things you can do. So wrapping up, going forward, the code is public. It's right there, github.com/mittdci/Utreexo. Recently, so we're sort of at the point where it syncs, checks signatures, checks proofs, can do it on mainnet, although it defaults to testnet. I definitely don't think you should use this for real money yet. There's still lots of things left to build, but it does sort of work, and we're working towards sort of a beta or alpha or whatever release soon, where we're sort of telling, hey, people, download it and try it out. So hopefully in the next few weeks. But even if you want to, if you can program and compile today, go. We don't have any binaries up right now, but the code is at the point where if you compile it and run it, it works. Asterisk, works. But yeah, and because it's sort of getting to a point where you can use it, there's definitely several people who have started contributing on GitHub, which is really cool. We do a weekly development call Tuesday mornings Eastern time. There's IRC channel, Utreexo on Freenode. So, and also just ask questions, message me, ping me on Twitter, whatever. Hopefully a lot of people are interested in it and want to start working on it. I think it's pretty cool, and hopefully, I don't know if I can take questions. I'm going to here. Great talk, very interesting. Okay, cool. Hey, people are interested in it. Cool, that's great. Dan, okay, well, if there's no questions, then we're good. But if there are questions, type them in the chat. I can read them. Pruning a blockchain, okay, so Durden, it's not called pruning. So there's already pruning, and pruning's been there for a while. This is sort of the next step. You could think of it as like pruning the entire state, but yeah, we need to think of good terms for this. I just call it Utreexo because it's like a cheesy pun on UTXOs, and there's a tree of them. State compression. Yeah, it's compressed. A lot of, so in Ethereum, very similar research they call stateless clients. I don't like that term personally because there's still state. It's not stateless. The state is much smaller. So you go from O of n to, in my case, O of log n, or in some cases maybe O of 1. But to me, it's like, well, it's not stateless. You still have a state. Allowing people to use it without downloading the whole chain. Okay, that also, you still have to download the whole thing. I mean, you could skip it. So you could say, I'm going to take some point in the blockchain where someone gives me a Utreexo accumulator state and say, okay, I believe this, and I trust that everything that happened before this is valid, and I go from there. But the default is you still do the entire mainnet sync, so you still have to download the whole 300 gigs and verify it, but then you throw it away. You sort of throw it away as soon as you get it. You download a block, check it, and then toss it. And then the only thing you're writing is that, yep, okay, I'm on the next one. So it's a weird, okay, history shredder kind of trash compactor. Yeah, I mean, it is kind of funny to think of the blockchain as trash, but it sort of is. Like, you don't want it. You don't want all this data. Mimblewimble is an interesting model too, where you can, in a different way, throw away the blockchain state data. And I haven't looked at it in enough depth, but I think this does mesh really well with a Mimblewimble type synchronization. Wait, I'm the last person, right? So I guess it's over. Where is all the doc? Good question. So there's some docs in there. There's a paper. So if you look on ePrint or you just search Utreexo, the PDF, the paper's there, and that explains mostly the accumulator. But yeah, we're working on documentation. That's actually part of the call tomorrow morning. We're talking about like writing it all up. There is comments in the code and there's some readmes and stuff, but it's not enough. There's readmes and there's comments and then there's the whole paper. But as we've been sort of working on it and developing it, there's new things that come up and it's like, oh yeah, this is how this works and stuff. But if you do look at the code or, compile it and play around with it and you have questions and say, hey, this isn't documented, put an issue on GitHub and I'll try to write more about it. Has been happening. There's someone on GitHub who often asks like, hey, how does this work? And so, okay. Yeah, I guess it's over. I don't know. I don't know if there's any like cutoff point. Okay, well now is I guess the time in real life where I would walk off the stage or something and talk to people and shake hands, but I guess instead I can go chop some more wood behind me or something.